Alright, so we get to the end of Chapter 2, 2.3.7, where we end up looking at estimating area with rectangles, but specific type of rectangles here is with midpoint rectangles. And this is going to build on the concepts we've learned with left and right. This is going to be kind of an extension of it. So, if this will go in section 2.3.7 at the bottom, say we have a curve, and we will call this curve f of x, and then we end up setting a domain on this, so we'll restrict it. We'll look at it on the interval a to b, and then we're going to look at, we'll divide this into three rectangles here. So here's our first rectangle, here's our second, and here's our third. And it's not to scale, which is fine, but this is more just to define that the midpoint now defines the height of our rectangle. Alright, now if we're going to write this in the notation we've been working with, let's say the area of function f on the interval 1 to 4 is equal to the summation of, now this is going to be the same as left endpoint, so we're going to start at 0 and we'll go to one less than whatever our subscript is, delta x times our height, which is f of x of k, plus delta x over 2. Now this looks very similar to what we were doing with left. We have our base, and we have our height. So we could call this sigma starting at 0. This looks like a left endpoint rectangle. The difference is here with the delta x divided by 2. What this allows us to do is it allows us to find the midpoint on that interval, and we'll unpack that with the number line. Okay, so this should look similar. Now, on our next slide, let's do an example together. For f of x equals x squared plus 2, find the area on the function 1 so then x, which is less than or equal to 4, that's our domain, using 6 midpoint rectangles. Now we're going to break this down into parts, and it's going to follow the same process we've been looking at. So our first step here, we're going to find your delta x, and if we're looking at the interval 1 to 4, we're going to find that distance. So we're going to do 4 minus 1, it's a distance of 3, divided by how many rectangles, which is 6. 3 over 6 is equal to 0.5. Here's our delta x. Second step here, after we find our delta x, is to find our x of k. And some of you I know will be able to do this without drawing out the number line, but I think it's helpful to do it, and just so you see it. So we're starting at 1, we're ending at 4, we're dividing into 6 intervals. So we have 1.5, 2, 2.5, 3, 3.5, and 4. And it doesn't have to be to scale, just more to notice the patterns. X of 0, x of 1, x of 2, x of 3, all the way to 6. And remember, this is our k, and our numbers represent our x of k. So we want to establish a relationship between k and x of k. So x of k will equal, it's going to be linear, so you're going to have your delta x, which is your slope, which is 0.5k, plus our beginning value, which is 1, is See, this is 1 plus 1. Now, that looks exactly like left or right endpoint, but because we want to find the midpoint, we want to find that number right in the middle. We're going to actually end up adding delta x over 2, which will be 0.5 over 2. Another way of saying that would be adding 0.25. So our final x of k will equal 0.5k plus 1.25. Now this should make some sense if we look at, use a different color. If we look at this point is, sure enough, right in the middle, 1.25, then we go to 1.75. That's going to get me right in the middle, 2.25 of those intervals. That's where we want to be, and our delta remains the same, 0.5. Good. All right, so our last step here is to find our f of x of k, which is our height. We're going to find f of x of k. To do this, we'll use our f of x. If f of x is equal to x squared plus 2, then f of x of k will equal parentheses squared plus 2. Now what goes inside the parentheses? We're going to take our x of k, drop it right in. So it'll be 0.5k plus 1.25. And this will be our final expression with the squared. Write it in there so you can see it. And it'll be good to have parentheses around this. Okay, so that is our entire height. For our final summation, will look like this. Sigma, and it will be good to use parentheses here, 0.5 times, that's my delta x, 0.5k plus 1.25 squared plus 2. And I'll show you why I have so many parentheses here. Got a couple things going on. 0.5 is my base. And all of this is my height. And then we have to look at my upper and lower bound. This will stay the same as left endpoint. So our k is 0. Now if we look back on our last slide, it's the same as left endpoint. We're going to be going from 0 to 5. So 0 will be my lower limit, my upper limit will be 5, and that will give you 6 rectangles. Now this is for midpoint. Be careful when you put this in your calculator to make sure that you use those parentheses to separate the base and the height. Now, it's helpful also to do this for left and for right. So I'm going to write the sums for left and right also, and then we can compare and contrast the differences. So for left, summation again, nothing changes with the upper and lower limit. Again, it's 0.5 times parentheses 0.5k. This is where it changes. Instead of going to 1.25, it will just go to 1. And then that's our final. Then for our right, we are going to shift it over 1. K equals 1, going to 6. 0.5 times 0.5k plus 1 squared plus 2. And we'll close this one off. So now we'll identify what's different. With the midpoint, the difference is right here in the 1.25. And then for right endpoint, since we're moving all the rectangles over 1, it will be in the lower and upper bound. Now all three of these will give you different answers. I don't have the exact answers on me, but I think it's something like the midpoint is around 26. The left endpoint's around 23. I think the right's around 30. Now it's to a decimal, so these are definitely rounded, but again you'll notice that the average, or not the average, we shouldn't say the average, the midpoint is the best estimate of the area under the curve.